A system in the figure below is in static equilibrium. A concrete block of mass 225 kilograms hangs from the end of a uniform strut of mass 45 kilograms. A cable runs from the ground over the top of the strut and down to the block, holding the block in place. For angles phi equals 30 degrees and theta equals 45 degrees, find the tension in the cable, the horizontal and the vertical components of the force on the strut from the hinge. So this is an equilibrium system. We're told we're in equilibrium, and if we know that we're in equilibrium, that means that the sum of the forces has to be zero. More specifically, sum of the forces in the x direction, sum of the forces in the y direction have to be zero, so that our object isn't moving left or right or up or down. If it's in static equilibrium, the sum of the torques also has to equal zero, meaning our object is not rotating. The object in question here is the rod. You have the block is putting a force on the rod, the tension of the rope is putting a force on the rod. But we know that the overall the rod is what is going to be moving in this situation. And so we can look at what forces are acting on it to try and keep it from moving. We know that there is a force due to tension. There's a force due to the weight of this hanging block. There's also a force due to gravity, due to the weight of the rod itself. Then we always consider possible forces from the hinge acting on the rod. We can just assume that those forces are going to be to the right and upward. We always want to assume that they're there, and if we have any, if those come out to be negative or anything like that, that just means that they're in the opposite direction from what we thought they were. And so we can look at this tension, for example. All the other forces are straight up or down. The tension, we can look and say that if we have an angle phi here, then this angle must also be phi, because those are alternate interior angles there. In that situation, we can look at the sum of the forces in the x direction. If we look at the sum of the forces in the x direction, we have t cosine phi is to the left. There is a horizontal component of the tension that's acting to the left. There's also a component of the hinge acting to the right, so that's a positive amount, and that equals zero. If we look at the forces up and down, we have a component of the tension that is acting downward. We also have the weight of the block pulling downwards on the rod. We have the weight of the rod itself pulling down on the rod. And we have the hinge that we're assuming is pushing up. And looking at all of these negative, all of these weights pulling down, it would make sense that the hinge would have to be pushing up. In this situation, we know these values. We know the value of phi. We don't know t, we don't know fx, and we don't know fy. So right now we have two equations, but we really have three unknowns. We have the tension and the horizontal component fx and the vertical component fy, so we still don't know any of those values. What we can do then is look at the torques. For this rod to be at equilibrium, it has to not be moving left or right, it has to not be moving up or down, it also has to not be rotating. The natural place for it to rotate would be about the hinge. Why that also works really well is that if we consider torques acting about the hinge, then this force and that force, the two forces, the two components of the force from the hinge, don't contribute to torques about the hinge, because these forces are applied at the axis of rotation. So in that situation, if you say that your torque is the distance times the force times the sine of the angle between them, your distance is zero for these two forces, and so there's no torque associated. So what we can do instead is look at all the other torques that are acting. We know that we have a tension acting in this direction. However, if we want the torque due to that tension, that means we need the perpendicular component of that tension. And so we need to know what this angle is right here. Well, we know that theta is 45 degrees, and so this must be 135 degrees right here. If this is 30 degrees and this is 135 degrees, then we must have a 15-degree angle right there. And so that would tell us that the torque due to the tension would be the force of the tension multiplied by the distance at which that force is applied. That distance is the full length of the rod times the sine of 15 degrees. What we're doing here basically is we're applying that force, we're applying the force of the tension at a distance L, and this term here, T sine 15 degrees, is this perpendicular component of the torque. This is how much of the overall value of the torque is actually causing rotation. And that rotation from the torque, from the tension, would be counterclockwise, so that would be a positive torque. If we look at the other forces acting on the rod, we also have the weight of the giant block, and we have the weight of the rod itself. If theta here is 45 degrees, and these weights are both perfectly perpendicular, that tells us that this must be a 45-degree angle as well, as must this other angle must also be 45 degrees. And so if we're interested in the perpendicular component of the weight, we'll say that the force of the block is applied at a distance L from the hinge, from the axis of rotation, because it's the full length L of the strut. There is a total weight mg, but we only actually want this tangential component of mg, and so we'll actually have a sine of 45 degrees there. We'll also notice that this force is tending to cause a clockwise rotation, and so that means that would be a negative torque due to the block. The same is true for the weight of the strut itself. If it is a uniform strut, then its weight should be applied at L over 2 at the midway point. The force being applied there is mg, but if we want the tangential component of that force, we have to multiply by a sine of 45 degrees there. This weight of the strut itself is also causing a clockwise rotation, and so that has to be a negative as well. And the net torque has to equal 0. What we see here is that we have a common factor of L. It never actually mattered what the actual length of the strut was. And we can find that the tension will have to be we can plug in values. We know capital M is 225 kilograms. We know that little m is 45 kilograms. And we see that the tension here must be 6,600 newtons. Looking at our significant figures, it appears that we have 3, and so we could actually write the tension to be 6,630 newtons. However, even as we truncate the tension, we still want to use the full value of the tension when we solve for the other forces. Going back to our first equation, we can rewrite that equation to say that the x component of the force has to equal t cosine phi. We have a value for t. Phi we were given as 30 degrees. And so the x component of the force at the hinge is 5,700. Again, we'll use our significant figures. We can also use the second equation to solve for the y component of that force. And we find that the y component of that force is thus, and we can use sig figs there as well.